Hi, now we're going to talk about reaction types. We know what a reaction is. We know how we can identify chemical reactions. Remember, we're looking for anything that tells us it's a chemical change. Precipitate, gas formation, energy change, significant change in color, change in odor, those sorts of things. We talked about that last semester. We know why atoms bond together, and we know why they react with each other to break apart and form new compounds. Now we're going to talk about the different ways that they can do that. One way they can do that is through synthesis. Synthesis means to create, to come together. It's sometimes called a combination reaction. And that happens when you have two things, A plus B. They're separate things, not bonded, and you end up with one whole thing. You may have more than just two things. You may have three things coming together to form one thing. But the important thing is you have a bunch of reactants and just one product. An example of this is hydrogen plus oxygen gives you water. Several, well in this case two, reactants giving you just one product. Right? An example of this might be if you take something like a blank canvas and little pots of paint. Right now they're separate independent things, but we can put them together and create something new, a beautiful piece of artwork. That's a sort of like a synthesis reaction, right? We can also have the opposite of synthesis, which is decomposition, right? To decompose means to break down, and that's exactly what happens in a decomposition reaction. You start out with just one reactant, and you end up with two or more products. So here we've got sodium chloride, just one reactant, breaking up into sodium and chlorine. If you have more than two elements in your reactant, you might break it down into more than two things, right? But you're going to start out with one whole thing, like a whole pizza. But let's say you're eating with some picky people, right? So they kind of break that pizza down into its parts. You've got like the crust and sauce and cheese. That kind of stays together. But then they pick all the pepperonis off. And they pick all the mushrooms off. So now you've got one thing that you started with, one reactant, several products. That's a decomposition reaction. A third kind of reaction you can have is called a single replacement reaction. A single replacement reaction. This happens when you have an ionic compound, AB, in this case for single replacement or single displacement, is always going to be ionic, and then you've got something by itself. That something by itself is going to trade places with something in the compound, right? So, for example, we could have this girl. She has a flower in her hair, right? And we can think of the girl with her flower as a compound. But then she sees a different flower. And she thinks, oh, no, that flower looks much better. And so she could let it trade places with the flower that she already has. Right? So she ends up with the opposite flower in her hair. Now it's important to notice that I didn't let the flower replace, oops, that's not right. Sorry. She's going to let these trade places. So now she ends up with the opposite flower in her hair. Right? It's important to realize, though, that I didn't let the flower replace the girl. The thing by itself, in this case is orange flower, is always going to replace the thing that's like it. Okay? So if you have an ionic compound, if the thing that's by itself is a cation, it's going to replace the cation. If the thing that's by itself is an anion, it's going to replace the anion. Right? Let's look at some examples of this, some actual reactions. We could take something like iron sulfide, right, where we've got sulfur and iron bonded. No, that's not right. Ooh, I'm so sorry, that's not the right one. That's double replacement. We're going to get to that in just a second. Sorry. Let's look at zinc bonded to hydrochloric acid. Here we've got zinc bonded to hydrochloric acid. So we've got hydrogen and chlorine bonded together. But zinc all by itself. Zinc is a metal. which means that it's going to bond as a cation. So we're going to let the zinc trade places with the cation, with the hydrogen. And that's the product that we get. Right? Zinc is now bonded to chlorine, and hydrogen is now by itself, even though it started out the opposite way. Okay, let's look at another example. This time we're going to look at something that has an anion by itself. We've got chlorine by itself. Chlorine is a nonmetal. It produces anions when it produces ions. And we've got sodium bromide. Since chlorine is a nonmetal, an anion is going to trade places with the bromine, right, to form sodium chloride and bromine by itself. You might notice that the subscripts are changing, and that's because, remember, when you write an ionic formula, you have to balance out those ionic charges. And it might take more or fewer of one ion or the other in the reactants than in the products to make those charges balance out, but that's okay. That's where we balance the equation later. I know you talked about that in middle school, and we'll talk about that next. Let's look at one more example. Here we've got a polyatomic ion, right? We've got coppers by itself, and then we've got it reacting with silver nitrate, nitrate being a polyatomic ion. That's okay. We don't need to worry about it. We know that this polyatomic ion is an anion. We know that silver is a metal and forms cations. So we know that the silver and copper are the things that are going to trade places, right? So we're going to end up with silver by itself and copper bonded to nitrate. Okay, now we're ready for that double replacement reaction that I pulled out last time. Sorry about that. In a double replacement reaction, you've got something very similar going on. Okay, but this time, instead of having a compound with a single thing, you have two compounds reacting. Two compounds reacting. They are still ionic compounds, right? So A, B, and C, D are still ionic compounds, just like they were in single replacement reactions. And the cations are going to just swap places. So if we start out with a blonde girl with a blue flower and a red-haired girl with an orange flower, we would just let them switch those flowers to represent a double replacement reaction. So the blonde girl would end up with the orange flower, and the red-haired girl, sorry, I'm kind of running out of room here, ends up with the green flower, the blue flower. Right? So it's pretty much the same thing as a single replacement or single displacement reaction. You have two compounds now instead of a single thing with a compound. All right, so let's look at some examples of this. Move that out of my way. Now we're ready for this iron sulfide. We've got iron and sulfur bonded, and we've got hydrogen and chlorine bonded. When they react, the iron and the hydrogen are the cations, so they are going to just trade places. So we have iron bonded to chlorine and hydrogen bonded to sulfur. Let's look at one more example, this time with a polyatomic ion. We've got sodium chloride, sodium and chlorine, bonded to hydrogen and sulfate. Okay. Same thing's going to happen. We're not going to be concerned because we have a big formula. Even though it has a polyatomic ion in it, same thing happens. We let the cations switch places. So now we end up with sodium sulfate and hydrogen and chlorine. This is hydrochloride. Wow. Okay? Again, the subscripts change, and that's okay. We're going to balance that equation out later. But I just want you to see what's happening with the ions in the formulas. When you have a double replacement reaction, you often get a precipitate. Remember what a precipitate is. A precipitate is a solid that falls out of that solution that you started with. So it's something that started out dissolved in water, but when it reacts, the new product is no longer able to dissolve in the water, so it settles to the bottom as a solid. So now you have a suspension instead of a solution. Okay? One more reaction type, and this one is combustion. And you probably, just from the name, can predict what you're going to get with combustion. With combustion, you're going to get things burning. Right? With combustion, let me put down here so you can read it. With combustion, you're going to get things burning. And you're going to get the products. I'm going to start with some organic something. Remember, organic means it has carbon in it. That's all it means. And it reacts with oxygen to produce a lot of heat and light, right? To produce fire, basically. And the products, carbon dioxide and water. Okay, you're going to get water if there is any hydrogen at all involved in the reaction. If there's no hydrogen, then they can't form water. So this is the one reaction that you don't get water in if you just have carbon by itself. For example, if you're burning, say, charcoal or something like that, it's just pure carbon. React it with oxygen, you'll just get carbon dioxide. But if you have any other organic, then there's probably going to be some hydrogen in there. Here you've got ethene. Remember that from the end of our last unit. Reacting with oxygen to produce carbon dioxide and water. And since this is a combustion reaction, remember there's going to be a ton of heat and light produced. So that's what it means to combust. All right, so in summary, here's what you should have in your notes. You should know the 5 types of reactions. We've got synthesis and decomposition. Right? Remember, synthesis and decomposition are basically just opposites of each other. You've got single and double replacement, sometimes called displacement reactions. You'll hear both of those terms, replacement and displacement. Single and double displacement are also very similar. Single displacement means you have a single element with a compound, and double displacement means you've got 2 compounds, but still you've just got the ions changing places. Combustion, so what we just talked about, where you have fire. An organic plus oxygen gives you a lot of heat, light, carbon dioxide, and water. For each of these types of reaction, you need to know the name, what happens, the general formula, right? The one that had like A plus B yields AB, or AB yields A plus B. And then you need to have some example reactions. You will be expected to be able to look at a reaction written on a piece of paper and tell me what kind of reaction it is. So be sure you've got some examples of each type of reaction in your notes. If you don't have all of these things in your notes, please go back, listen again, and add to your notes until you have all of the information and you're comfortable that you understand the material. If you have any questions, write them down for me so that tomorrow when you come to class, I can answer them.